All right, recording is rolling. Welcome to Monday, August 14th. Hope you guys had a great weekend. Haven't seen you guys since Thursday. Yeah, hope you guys had a good summer for that matter. Always good to reset. Yeah, so we're just trying to get the ball rolling. So Thursday we had to cover stuff, like fire drill and procedures and all that stuff too, right? I told you guys the story of like how technology got rolling. We got to about the scientific revolution, and then Newton wrote Principia, laid down physics, and that's about where the bell rang. So there's more stuff I want to tell you guys, stuff to do with physics and keeping a planner and organization, the whole bit, right? Now, I did have some other stuff lined up today, but I think it was a little bit overly ambitious. I'm gonna have to bump some of these activities. So what I have for 5 days might take me like 6 or 7 days, but we're gonna do what we can. But here was the plan anyway. This activity we're gonna bump to another day. It has to do with like measuring and graphing and stuff, right? This week I'd like to do with you guys some very fundamental groundwork like scientific method, scientific notation, measurement prefixes, unit analysis, dimensional analysis, unit conversion, algebra, right? So like equations like solve for x, if there's a coefficient, you divide by the coefficient, take square roots, right? All this stuff, quadratic formula, right? Some basic graphs, right? So like y versus x, can you like graph a parabola? Can you graph a straight line, right? So really fundamental to this class you're going to be doing all the time. If you're a bit rusty on it, well, that's one of the reasons we're doing this. Right? Also, I need to cover with you guys vectors and trigonometry. So, do you guys remember like sine and cosine? Right, sine and cosine. Okay, maybe. Right now, if that rings a bell from the very distant past, or like, oh, I'm super rusty on that. Okay, that's why we're covering here. There's a very specific application of that in physics, which is components, vector components. So, suppose I have some vectors like going up and to the right. I want to quantify how much up and how much to the right. Well, if I know this angle right here, then say like how much to the right, right? That's like a cosine component from playing off this angle, right? If I want to know how much up, right? It's like playing off the sine component, right? So teach you guys components, touch on sine and cosine. I'll have you guys measure with protractors, and we'll do like a lab type activity with that. Okay. This Thursday and Friday, I want to do a mechanical engineering project with you guys where there's some index paper in blue, and we're going to construct something with moving parts. It's called a Geneva drive. You can use it in like classic TikTok watches if it says Geneva drive in it. You can use it for projectors type thing. One of the purposes of this is to have you guys get your hands on stuff and construct something that looks complex, but you see how it actually breaks down to fundamental parts, which is part of the thought process, I think, in physics, maybe something you can get out of physics. Right. If you haven't yet, then sign on to Google Classroom with that code. Was anybody not here Thursday? Needs those papers? Not here Thursday? Okay. All right. So you guys have those papers from Thursday? Right. Yeah. So go ahead and join Google Classroom if you haven't yet, and post a bunch of documents there. But here, that's part of my presentation too. So let me go ahead and skip over here. All right. And back to this presentation. All right. So back on Thursday, you guys had just one name card. You guys wrote your name, and I made a seating chart for rows, right? But now you have you guys in teams. Right? So go ahead and write your name if you like your desk. If you like your desk, then write your name. So this is period 7. So go ahead and write there. I will make a seating chart for that, and I'll have 2 seating charts. Some days I'll have you guys in rows. Some days I'll have you guys in teams, right? All right. So pretty close to the end of the story back on Thursday. You might give a small recap here. Isaac Newton is back in his house, maybe in the background there. That's his house in the back where he grew up. Maybe looking at that apple tree right there. Watches an apple fall from the tree and has an epiphany that, well, eventually leads him to lay the groundworks of physics and coalesces into this class. He's asking, why does an apple fall? Right? The Earth must be pulling on it, but what's the nature of that? He looks up in the sky and sees the moon and says, hey, does the moon also fall? Right? Is the Earth pulling on the moon the same way it's pulling on an apple? Right? And he realizes that, oh, hey, if the moon was moving to the side fast enough, it would actually be pulled towards the Earth, but it would never actually get any closer to the surface because it's like falling around the curvature of the Earth. Right? He's the first person to make that connection. Before this epiphany, the conventional wisdom was, well, there must be terrestrial laws and celestial laws. And terrestrial things want to move in straight lines and slow down, come to stop. And celestial things want to move in circle type patterns and go on forever. And Newton says, no. Actually, there's one set of principles driving all this motion. Right? He makes this unification that no one else makes. So goes back to his room, does a bunch of experiments, likes collisions and momentum, especially, he comes up with the laws of motion, gravitation. It's a whole new branch of mathematics called calculus to back up a lot of his physics work. Calculus has to do with rates of change. Does work with optics, and then just throws us all to the side. Says, okay, that's for my own personal curiosity. Years go by, and then in 1682, this comet flies by, Halley's Comet. Well, it wasn't called Halley's Comet at the time, but it was about to be. So people were looking through the records and realized that every 70-something years, this comet comes up again, plus or minus a couple of years. It's kind of a wobbly orbit. Right? And everybody's trying to figure out, why do these comets have these highly elliptical orbits, or why does anything move in elliptical orbit? Right? Now, weirdly enough, people had studied astronomy precisely enough by this point to realize that even planets don't quite move in circles around the sun. It's like slightly elliptical orbits. Right? You can kind of approximate circles. It's pretty close, but not exactly. But comets are highly elliptical. They go way out past Pluto, way close to the sun. Right? So what's the deal with ellipses? Nobody can crack this problem. So Halley's one of the scientists trying to figure this out. He gets word of this guy, Isaac Newton, goes and talks to him. Right? And Newton says, oh, yeah, I figured this all out. And he lays out all the work about universal law of motion and gravitation and calculus. And Halley's having his mind blown. So you got to publish this. So Newton does. Here's Principia. Here's some of his handwriting here. Here's some of his work on optics. You guys see this nice refraction right here. Right? So here's some of the main topics in Principia, right? Got parts of calculus, laws of motion, gravitation, optics, right? And this is where physics really coalesces into a subject, and it's expanded since then, right? So a lot of things have been added and written for different contexts, different audiences. But here we go. Now we have physics, which is the study of the laws of the universe that govern matter and motion in the universe. Right? So yeah, so it's what you guys get to learn is like what makes everything tick. What's the rules to everything? Okay? Now here's the updated version of Principia. I have 3 different versions of it in this classroom. Go over every single one of these. So this blue book on the far left, Conceptual Physics, is really geared towards students who are not very good at math. So it's conceptual oriented. But I really like the way that the author presents a lot of the information. So I will draw materials from the set of materials from this author, Paul Hewitt, sometimes. The book in the middle, Physics Principles and Problems, is the main physics textbook for you guys for honors physics. So I think it's pretty standard. It checks all the boxes. Some things I like in it, some not so much. So if I like it, I'll maybe draw stuff from it. And if not, then I'll come up with something else. Okay. This book on the far right, college physics, this is mostly for like AP physics, so I probably won't pull that out too much with you guys. Okay. And now here's the deal with the number of copies. The school is getting bigger and bigger, and we got 4 different physics teachers at this point. So I only have about 30 or 40 copies of each one of these books, which is enough for a class set and a few extras. So I can't check out a physical copy to every single student. We don't have the numbers, right? But usually every year I might have just a couple of students who do request a personal copy. So if you do, let me know, and I might be able to get one to you, and just do that for a couple of students. Right? Now the school does have permission to, it has license to give you guys digital copies. So I have uploaded digital versions of these to Google Classroom, and you can access those there. Oh, speaking of which, right now that's a screenshot for Google Classroom, but let's pull up the actual Google Classroom. So let me switch over to you guys. That's AP. You guys a little bit different. Honors, classwork. Okay. Hopefully you've started to explore this. I uploaded some new stuff over the weekend, so let's take a look. These first few files, the district calendar, curriculum syllabus, some review pages and variables and units, and in the AP physics one, equations page. Okay. Now all those I printed out and gave to you guys back on Thursday, so you guys already have those. Also, I have slides in the PowerPoint, so I'll go over this more depth here in a few minutes, but let's take a look at the other ones. Got University of Colorado Boulder interactive simulations. So if you want to run some physics experiments just on your computer screen, you can do that. Let me give you guys an example of something I sort of remember being there. You guys see a poster here that involves like a cannon blasting a ball off a cliff? Is this? Right. So what if I had the question like, where is the ball going to land? What is its horizontal displacement going to be? Like how far from the edge of the cliff is it going to land? Right? Do you think that might have something to do with the blast speed? Like how fast the cannonball uses cannon? Yeah, right. Do you think it has something to do with the height of the cliff? Do you think it has something to do with the gravity field? Like, what if you took that whole system to Mars where the gravity's a lot weaker? Do you think Cannonball would go maybe a little bit further? Okay. And one of the interactive simulations here involves pretty much that. And you can play around with the variables, slide them up and down, change the height of the cliff, change it, right? And see where the ball lands. And then you can take all these equations that you're going to learn in class. You can run the same thing just on paper. Maybe it might take you a couple pages. And realize, oh, hey, the ball landed exactly where the math says it should. Right? Next, there's a couple files here, a couple of PDFs, physics posters. So, okay, so you guys see some posters hanging in the room. I'll give you guys a quick tour of these. So all the ones on this wall over here and those three up there are just like fundamental to the class. So we're talking about things like basic algebra, trigonometry, and components, scaling, basic graphical relationships, units of measure. Right? And so it's going to take about the next few days to look at that type of stuff. Prefixes, scientific notation. Right? Then all the ones hanging right in front of you right here are kinematic motion, which comes in two parts. We got linear motion more on this type side, right? Which is just motion along one dimension. So it could be back and forth. I think you got like some cars driving forward kind of deal, maybe braking to a stop, maybe speeding up, right? But if you take something, throw it straight up, it comes back down. Ooh, I bet you could take these equations and describe that motion with that, right? Oh, but it's all along one axis, right? Straight up, straight down, right? Over here, more towards this side, is getting into projectiles. So now we're opening up two dimensions. Now we're blasting this cannonball, and it's going across, and it's also being pulled down at the same time, right? It's the same equations, though. It's just nothing, right? And then all those in the back are the unit we're going to do after that, which is like forces, free body diagrams, Newton's laws of motion, right? Like, why would something accelerate? I throw something up. Why does it come back down? Right? Versus we're going to start kinematic motion with describing that it does, and then later I'm going to what's caused that. Right? And so that's the units 0, 1, and 3 basically, or 0, 1, and 2. If you want to peek ahead to stuff we're going to do later this semester, see like energy, momentum, and rotational dynamics, that's all here. Right? This other file gets into what we're doing when you guys come back in January. Right? So I do encourage you guys to download as many of these files as you like, have them on your laptops, and look ahead. And like the more time you spend looking at these, the better you're going to learn the class. Variables and units. I do have but I gave you guys a printout back on Thursday, but this is a flashcard version of this. If you like flashcards, if flashcards are really helpful to you, then print this out and you got some flashcards for variables and units. Textbooks. So like I told you guys, Principles and Problems is your guys' textbook, although conceptual physics I really like a lot, so draw some materials there. There you go, you guys got some PDFs. And the guy who wrote this conceptual physics, his name is Paul Hewitt. He has a lot of really excellent demos that are just like usually a minute or two. I'm going to show you guys throughout the year. Maybe he explains things a little bit differently than I do, right? Right, so there's about 50 here, about 50 here. You guys will see these. If you want to download those, probably really convenient to have on your computer too. Again, just like 1 minute demo where you explain something like in a nutshell really well. Oh, look at this first day video. If you want to see exactly what we did back on Thursday, it's recorded. It's right here. You guys remember day 2 was laptop day. I didn't actually see you guys that day, but if you want to see in general what was going on, you guys might remember some of these. There's a nickname request form. I've got a paper printout right here on this desk. You need to go get that signed and bring it back. Something about the law or something. Right. Oh, we're going to get into algebra, trigonometry, stuff math that's really foundational to this class. So I will do some practice algebra with you guys, but we'll only take like maybe part of a class period to run some algebra equations, like solve for x kind of thing, right? Now, you might feel really comfortable with this, which is really good if you are, right? Or you might feel like really rusty on this, but that's why we're taking some time to do it, right? If you think you need extra practice, then, well, here you go. Here's a file, just some basic algebra equations, and you solve a bunch of stuff, right? We'll do some of those, right? Circles for measure. Yeah, I had a whole activity lined up today, but didn't have time for it. So I'll bump that to sometime in the future, right? Have you guys take some string, measure some circles, create a couple of pretty cool graphs. We'll get there. Okay. Paper protractors. Now, I have some plastic protractors in this class that are clear so you can see through them. I'm gonna use those for an upcoming lab, but if you're at home and you need a protractor, don't have one, boom, print that out. Now you have a protractor. Trigonometry lab. That's kind of all triangles, angles, sides. So all that sine and cosine stuff that you probably learned in a math class and you're like plugging numbers on a screen, right? We're going to do the science version of that. And the science version is empirical measurement. So I'll have you guys break out rulers and protractors and record numbers and realize, oh, hey, this does line up with the sine and cosine on the calculator, right? Here's some extra trigonometry practice. Right? It's good to, I mean, more stuff you know, easier it's going to make it, right? If you can work your way around a triangle, they give you some very basic stuff about a triangle, like, oh, here's a couple of angles and one of the sides of the triangle. Can you figure out everything else about the triangle? Can you do some geometry? Right, so there you go, some extra stuff, right? I went ahead and also uploaded stuff even further into the future over this last weekend. So some upcoming labs related to linear projectile motion, got some algebra-based questions. Here's linear projectile, and also some conceptual questions, linear projectile. I know these are tiny thumbnails. Feel free to download these and look at them too, right? But in a nutshell, what's going on, these algebra questions will give you guys some basic premise. Got a cannon on a cliff, and then a bunch of numbers. Here's the height of the cliff. Here's the velocity of the cannon. Here's the gravity field of the planet, blah, 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 right? Can you figure out where the ball lands, right? Something like that. I guess that would be a projectile question, right? So very, very like math-oriented, heavy equations, versus these conceptual questions. Even just from the thumbnail, you can see that they're more like word-oriented, right? So they give the core concept and they're pretty light on the math. These make really excellent Kahoot questions. So if you guys are bringing your laptops to class, then, well, get some Kahoot practice with these someday, right? Okay. Oh, and here's some problems from your textbook. I think if I were writing your textbook, I would have organized these chapters a little bit differently. So we may not even pull out this page. I don't know, but well, I got something there for you guys anyway, right? I may go a different way up with those chapter stuff. All right, so there's Google Classroom. You guys can have fun exploring that. All good? All right, let's move on. Right, curriculum syllabus, or sorry, that's AP. Let's go to you guys. Okay, so curriculum on the left side here. So we're gonna do intro stuff, algebra, trigonometry. Okay, we're eventually get to kinematic motion. So yeah, that's all these posters hanging in front of me. Then we'll do forces, Newton's laws. That's all those posters hanging back there. Then the unit after that, okay, I used to not teach it this way, but I've come around to this, and some textbooks do it this way, and I think this is actually a good way. There's a few topics they put together: circular motion, gravitation, orbits, right? So circular motion, put a ball on a string, throw it around a circle, right? You think the tension in the string is holding in a circle, right? What is that tension? Do you think it's related to the mass of the ball? Do you think it's related to the speed of the ball? Do you think it's related to the radius of the circle? Right? There's equations that go along with these things. Right? Universal gravitation. So anything with mass pulling on it, right? The Earth and the Moon are pulling on each other, for example. Right? You can put those two ideas together and get orbits, right? And that was Isaac Newton's epiphany, where he sees the apple fall, sees the moon, right? Starts writing stuff down. After that, we'll look at energy. There's this kind of abstract idea where you, the scalar value that's conserved, you can set up equations and sometimes solve things more efficiently through this conservation of energy method. Momentum, anytime you see collisions, I'll break out the collision carts one day for you guys do a lab with that. Momentum is conserved, a lot like energy is conserved, but it's a vector value. That should take us to about Thanksgiving break. You guys come back from that break, we'll hit rotational dynamics. Now, there's some overlap between rotational dynamics and the circular motion back here. So this is kind of, circular motion is kind of a preview to this rotational dynamics. But that's good because rotational dynamics is so hefty. Yeah, go ahead and grab that green passive there. That it's good, I think, to break it up a bit. Right. Yeah, there you go. All right, that'll take us to midterm. Then when you guys come back from Christmas break, we'll do harmonic motion. So we got pendulum swinging back and forth. Then we'll do waves, sound, light, optics, thermodynamics, some basic materials and engineering, electricity and DC circuits. So how do you guys wire some circuits together, measure what's the voltage, what's the current. All right, how they design the schedules. We've got spring break like later in the year than we did last year. I don't know what that's about, but I might have to split this up and we start here and then we'll go to spring break and then come back and finish it. I don't know, we'll see when we get there. Okay. I'll do some magnetism, electromagnetic induction with you guys, theory of relativity, quantum mechanics, and that'll take us to the final exam. It's gonna be a good year. Here's Brevard School calendar. You guys got this printed out. Tells all the hurricane days and all that. All right, this page. So here's another one, double-sided, that I printed out for you guys. So you guys already have. Gave it guys back on Thursday. Now, this I originally designed as a review page for my AP students, but it is really handy. So the topics go in order approximately the way we're going to study them. What's say a flag that would tell you that some question you get is within that context. Maybe if you had a huge standardized exam, you want to know like, how do I know it's conservation of energy versus momentum or something, right? So there's some flag there. Right? Oh, a bunch of classic formulas that are involved in each one of these topics. I think these three equations right here are those three in the top left poster right there. Same thing, right? What are some really classic fundamental examples? Like for every single one of these topics, if I had to just pick a couple examples, things to look for, they're right here. It's like in a nutshell, right? This is going to be a lab. This is going to be a lab. This is going to be a lab, right? So a bunch of lab opportunities up here, right? Some really common graphs. You're going to see graphs all over the place. You're going to be drawing lots of graphs with a bunch of your labs. So if you're coming from a pure math class, then you might say this is like, oh, y versus x. Got a y-axis and an x-axis. But in physics, these represent variables. So it might have velocity measured in meters per second versus time measured in seconds, for example. Or how about force measured in newtons versus displacement measured in meters, right? So these axes are going to have represent variables, and they're going to have units attached to them. And then different properties of the graph will tell you different physical information too, right? Like each specific coordinate could tell you something about like, okay, goes so far over on that variable, that represents so far up on that variable, right? But the slopes of these lines tell you instantaneous rates of change, right? Like rise over run, right? Like unit per unit. Right? And the areas under the curves tell you something that's accumulating for somebody. Like if you see anything that's like shaded in on this page, right? Like if you push for some force for some distance, then you've done some work measured in joules, like you put some energy into that system, right? So in that, now area has something to do with base times height, right? Maybe if it's a triangle, it's like 1/2 base height, right? So the units also will carry. So newtons times meters actually represents some number of joules, right? Paper's double-sided. So on the back, I got stuff about electricity circuits. Got trigonometry vectors here, some references, prefixes, units, basic graph shapes. All right, there we go. Oh, here's another page that you guys have back from Thursday. Got variables and units. So these might be, I think it should be all the variables you see in this class, maybe with a couple of exceptions. Right? So like x could represent displacement. Sometimes x is position and delta x is like a change in position. They call it displacement. Usually I just write x. Right? Some textbooks do delta x. Right? And that can be measured in meters, for example, because this class is going to be metric system, which you probably also did in your other science classes. Right? For every single one of these, I gave you some kind of, well, most of these, I gave you guys some kind of note on these. Maybe something in a nutshell that's fundamentally important or good to know, or maybe like some misconception that I want to clear up. Oh yeah, everybody thinks this, but you got to know this, that sort of thing, right? So good to read these. I'm just pointing these out to you right now, but you know, sit at home and really examine these, and hopefully you could enjoy learning a lot about these. It can help you out as we're going forward, right? And also a classic example formula for every one of these. I do want to point out the letter M is used all over the place in physics and has completely different context. Like here, it represents meters as a unit. So I could say x is equal to 5 meters, for example, right? You'll see that all over the place. And let me finish this point I'm making, right? But down here, this M is a variable to represent mass. So I'm going to say mass is equal to 2 kilograms, right? Something like that. In another context, it could be the prefix milli, like millimeters, right? 7 millimeter, radius is 7 millimeters, right? And in other contexts, sometimes I say y equals mx plus b. In that case, it represents the slope of a line in an algebra sense. There's only so many letters to go around, and they start recycling them. So be careful about that one, especially. In this class, you won't see naked numbers. Every number has a unit attached to it. So if I say like I walked a distance of 5 what? Okay. 5 meters, 5 kilometers, what are we talking, 5 inches? Right? So don't say the distance I walk is 5, because that doesn't tell you anything. Also, don't say the number of meters I walked is 5. Right? Okay, so in this class, it's going to be like x equals 5 meters. Okay, something like that. And then all these work like that. Oh, and then here's later on. Okay, got rotational stuff. You can see a bunch of Greek letters here. Got electricity stuff. Got some operations down here. All right, AP equations, again, really for AP, but I did give this to you guys, so if you want that as reference, pull that out too. Okay, hopefully you did this over the weekend. Oh, yeah, go If you haven't done this yet, then please do write this in your planner and take care of this. Go ahead and join Google Classroom so that the day rolls around, one day you catch the flu and you're really sick, and then you get well enough where, well, I can at least roll that video. Hey, oh, thank goodness I joined back in the day, because that's all I can do is just reach over and press play. Right? And then anything you need to see, anything you need to download, you lose a paper, you need to see what we did in class, right? Google Classroom. Right? Don't worry about the AP stuff so much, right? Google Classroom. All right. So far, what have we got? I did procedure stuff with the guy, like fire drill procedure stuff on Thursday. I told you guys how, say, for 250,000 years, we're just like living and breathing with the earth, running around these hunter-gatherer tribes, and then we start to invent agriculture and think more abstractly, come across a scientific revolution, physics is founded. All right, so now what's some like kind of direct stuff you can do with physics? Why would you take this class, and what can you directly do with this? What are some jobs that directly link to physics? Okay. So one is any kind of engineer. That's what I have here. It looks like some kind of mechanical engineer design going on right here. Got mechanical engineering if you're anything with robotics or like factory parts. How about civil engineering if you're doing things like roads, buildings, drainage systems? Got industrial engineering, electrical, right? Any kind of engineer. This class you're taking right here the next year, it's going to be foundational to like pretty much everything you do for like your career on out. You're going to be thinking physics. Right? Last year there were a couple of Navy guys came through and were telling their story about they were working on, I want to say submarine or aircraft carrier. All the U.S. Navy submarines and aircraft carriers are driven by nuclear power. So if you're operating a nuclear engine, you got to know stuff about physics. Got to take a bunch of physics classes to know how that works. Right? They were also saying too, if they ever retire from the Navy, that they had these stories about all these private firms who were like begging for them to work at their firms for like $100,000. So man, that could be a good route, right? If you want to go that way, right? Maybe do a few years in the military and take a huge salary somewhere. Could be, right? This one in the middle of the top. This is a snapshot at Lawrence Livermore Laboratory, where just in the past year, they were finally able to create a fusion reaction, a controlled fusion reaction, so not like a runaway H-bomb, right? But where they got more energy out of the process than they put into it. Right? Now, this particular method, they're using a bunch of lasers to try to fuse hydrogen into helium. Like, right now, you guys know we're in this slow-moving planetary crisis, this energy crisis, where like most of the energy that we're using, and there's a bunch of energy being used in this room right now, right? We got air conditioning, we got projection, we got lights, computers, even just like the food you eat, the agriculture, there's a whole process that goes on behind, right? Most of that comes from some version of fossil fuels. That's bad for a couple reasons. One is that we're running out. Two is that they pollute the planet like crazy, and we got climate change, ocean acidification, the whole deal, right? So what's ultimately going to get us out of this problem? I mean, at the end of the, there's different stopgap measures and whatnot, but at the end of the day, the answer is just going to be fusion. And we're so close. We're like right on the cusp, but we don't have any commercial fusion plants yet. But it's gonna. Hey, maybe you'll be a scientist who can work on that problem, for example, or like any of these other ones. Right? Particle physicists over at Large Hadron Collider, smashing together particles at near the speed of light and gathering statistical data. They can get information about quantum mechanics, about the fundamental fabric of the universe. Going to be a rocket scientist. Ooh, right? In the past few weeks, there's been a claim. Somebody, I want to say in South Korea, claims that, or some scientists or scientist team, that they have discovered a material that can go superconductive at room temperature, which would be a huge story if that's true. I think it's developing or up in the air right now, but there's new science and technology that's being developed all the time. So that's definitely cutting edge there. Here I got gravitational waves on the fabric of space-time. Could there ever be a day? Future's a long time. We've only had writing for what, a few thousand years, it's millions of years to go. That could we ever have an understanding of the fabric of space-time so intimately that we're able to maybe engineer some kind of warp drive and just zip around the galaxy, maybe faster than the speed of light, right? Which we don't know how to do right now. Who knows? Future's a long time. It's an open question. Maybe it'll be a scientist make some kind of contribution to that. All right, so there you go. There's some examples of, especially if you're going to be an engineer, there might be a handful of you in here, or do some kind of military option that definitely need physics for, right? But hey, maybe you're thinking, ooh, I don't know if I want to do any of those things, but I'm still in this class, and what am I going to get out of this class, right? One thing I think is just a mindset of being able to take a complex problem and break it down into like first principles, like fundamental parts. You're like, maybe I have this goal, it's gonna be a huge project, you need to put this together. Maybe just like your brain being able to operate in such a way where you can break it down in parts and manage it and construct something new, right? But I also have the story. How are we doing here? When's the bell ring? 30? I think you're doing okay on time. You're okay now? Okay. Okay, what have we got here? I got calligraphy, I got an Apple iPhone, I got Toy Story. Do you guys know what the connection is for those three pictures? Where am I going with the story? Maybe somebody's going to figure this out. I guess. All right. How about this? See, Pixar and Apple. Same guy founded those two companies. And who was that? Aha, Steve Jobs. Yeah, you guys know this. You guys know where this is going. If you've ever had the chance to watch Steve Jobs' 2005 commencement address at Stanford University, it's like one of the best. So I'm going to steal part of his speech here because this point I'm going to link back to like, well, what am I doing in physics if I'm just interested in art history or something, right? So one of his stories he's showing here is he graduates from high school, he's going to go to college, and his parents had been saving money all his 18 years that he was with them just to send him to college. Whole backstory to that. So he goes to college, and he's not really sure what he's there for or what he's doing, right? No, eventually, of course, spoiler alert, starts inventing some of the first personal computers in his garage, but he doesn't know that at the time. He's just there back in the early 1970s and doesn't know what he's doing. What he does know is that all his poor parents' life savings is being drained towards tuition, right? So he makes a really bold move, which is he drops out of college, but he sticks around campus, just like sleeps in friends' dorm rooms and stuff, right? And he does something that's really cool to do, especially at large universities, which is like if you guys ever get the opportunity to attend a large, say like a 4-year university, one thing that's really cool is a lot of those lecture halls have like 200-300 people in them, and so you could just like go sit in the back and like learn about like, hey, I'm gonna learn about African history today, and like nobody would ever know. You could just like learn stuff, and so that's what he would do. He would just say, okay, well now I'm liberated from the shackles of having to, okay, well, I'm this major in this program, and so I have to take this class, and I don't even know what I'm doing. Okay. I'm liberated to just take classes that just look interesting. I mean, I'm not going to get credit for them, but I can just sit back and learn stuff, right? Which is kind of the point of learning. Right? So one of the classes he's interested in is called calligraphy. So we're talking about like the art of fonts, like handwriting, like fancy letters, sort of thing, right? Now, what practical application could that possibly have to learn about calligraphy? Well, there isn't an obvious answer, and there wasn't at the time either, other than just his heart tells him, this is interesting, this is what I want to just sit back in the class and maybe like wear some shades and incognito and just learn. Okay? Well, lo and behold, many years later, when he and his team are in his garage trying to put together the first personal computers, one of the many problems they have to crack is how do you create a legible font on a pixelated screen, right? Easy to take for granted nowadays, but back in the day, that was one of the problems, right? Right? How do you create a font that you don't just read and just get annoyed and aggravated? Oh, right. So, and then all those principles of letter design come back. So the takeaway is that you can't always connect the dots going forward. I mean, in a sense, you can have like some goals and some ideas what you want to do, but really, if you follow your heart and just learn things because you're interested in them, a lot of times doors will open that you didn't even know were opportunities until you were there and just took advantage of just learning what you wanted to learn. And this is a classic example of that. Okay? So yeah, founds Apple and gets fired from that and starts Pixar. Oh, okay. So this right here, bunch of little tiny boxes. How many boxes do you guys see across? 52? 52. So what do you think every single box represents? Ooh, a week? A week? And okay. Oh, so what does every single row represent? A year. And how many rows down? About 89, 90, something like that. Ooh. Okay. That's math of your entire life. Yay. And maybe every single Saturday, you check off one of those boxes, and yeah, we are all in a slow march toward death. Let's see, this gold band right here, you guys are all right about there. Yeah, life's short, goes fast. So what do you want to get out of life, make of life? What do you want to experience? What goals do you want to have? How are you going to orient yourself towards achieving these things? Right. I'm short, right? So here's maybe one framework. I think, I mean, maybe there's lots of frameworks you can have trying to figure out, as you're like exiting high school, going into college. Um, I like this one. Maybe start with something like, what do you enjoy doing? Well, what are your maybe natural interests, right? And hopefully there's some kind of overlap between things you're interested in and things that you're good at, right? Maybe it's like we're looking at some kind of Venn diagram type setup, right? Right. Or maybe you have a natural knack where you could pick up such and such skill. Like I can say for me personally, I'm have a natural knack for math, but I'm terrible at learning languages, for example, right? So I couldn't be a linguist, but that's all right. I'm okay here. Right? But maybe there's a number of things that you love doing or are interested in, and it's like I could pick up this skill if I just like put in the time, right? So put in the time, right? Find a time in your day, put in your planner. Maybe it's not a class that's offered on this campus in the school, but it's something that you want to do, right? And then kind of the other side of this is maybe the more economic side is like, what does the world need? Like, what is there a demand for? And what can you be paid for? I guess like in the labor sense, there could be a demand for your labor, right? I think, again, this is just one framework of thinking about things, but I think if you can check all those boxes, probably pretty set to live a pretty fulfilling life, right? I think. I know this job, teaching physics, I definitely feel like I check all those. I mean, there's a ton of work that goes into teaching this class physics, but I'll work for you guys so you can get the most out of this class you possibly can, right? But there are so many people that just end up like working jobs where they feel like unfulfilled and they just hate going to their jobs and they hate wake up in the morning. Like that would be a terrible thing to have to get into, right? It's like wake up in the morning, it's like, I don't even want to go to work and what am I going to do with my life? But there's bills to pay and they just do what they got to do. And like so many people end up in that situation, right? Maybe most people, I don't know, but you guys right now, like at the tail end of high school, right? If you can somehow set yourselves up to do something you at least enjoy doing, then hopefully, help you guys set yourselves up in a good direction, right? So what do you enjoy doing? What skills do you want to develop, right? Maybe some of your high school classes are directly connected to that. Maybe not. Maybe it's something, some separate hobby you have to do on the side and make it happen, right? How does physics connect? Maybe there's a direct connection. I want to be an engineer. Boom, physics done. Maybe I really enjoy art history. Well, now it's maybe a little bit more abstract. Maybe it's like Steve Jobs and calligraphy, right? You don't know how the dots are going to connect down the line, but keep an open mind, learn as much as you can, and maybe you'll see something, and you'll learn something in class one day. Maybe it'll just be one thing. Maybe it'll be like one thing on December the 1st, and oh man, I'm really glad I wasn't sick and away from school that day because I learned something really valuable and I was able to connect it to something I really enjoy. Right? Is it possible you'll work a job that doesn't even exist yet? 20 jobs that didn't exist 20 years ago. All right, well, I won't click the link, but you guys, there's probably lots of internet articles about that. So again, it's really easy to lose context. If you're just like live in the water that you're swimming in, of like how fast things are ever changing, right? I mean, that's one of the reasons I wanted to take so much of Thursday and really hammer down the idea that like, for a good 250,000 years, we're just like running around as cavemen and don't really have much of a notion of higher abstract ideas. Like how fast things are changing, or like when I was back in high school, YouTube didn't even exist, right? So if you have like any ambition to do like something with like a YouTube channel or a podcast, like that wasn't even like a concept back when I was your age, right? Yeah, cell phones. I never had a cell phone until I went to college. I think it was like two people back in high school who had cell phones, and the big worry back when I was in high school was like, oh no, not cell phones. Somebody could ignite a bomb with a cell phone. People are weird. Right? But habits. Okay, so you guys got planners back in registration. You guys all have planners, right? Okay, please use those. Use those. If you've been in the habit of using them over the past few years, you know how efficient it'll make it. I mean, write down things that you want to do, right? So look, we get to the end of the day. I know every single day I go home and I'm just like wiped out, exhausted, especially as the year goes on, right? Like we get to like April, May, it's like I'm just working on momentum. I just do stuff because like, oh, okay, this is just my routine, right? But I open my planner. It's like, okay, yeah, that's right. It's like 5 or 6 things I got to do. I wouldn't even remember because my brain's wiped out, exhausted. But okay, I'm gonna sit down, I'm gonna take a break, I'm gonna eat dinner, and then I'll break this out and just start going through these, right? It might be stuff I have to do for school. It might be stuff that I just want to do, like personal projects that I just want to do like outside of my work. It could be, hey, maybe there's a TV show that comes up every Wednesday and you want to make a space and time for that. Great, make a space and time for it, right? Now there's a space and time in your planner, right? See, like if you're not organized, then it's just like scatter. You're trying to remember, and you're just making your brain even more exhausted, and then you procrastinate, forget, oh, that project was due tomorrow, right? But if you're organized, it'll really make your life like so much better. And you'll be able to do all the stuff that you want to do. Like it's not just schoolwork, right? Not to say this because I'm a teacher, right? But all the things you want to do, right? Um, if you're thinking back to the past, you're thinking, yeah, I haven't been a really great student last couple of years. I don't use a planner. I mean, yeah, sure, I kind of forget things sometimes, and I'm always frustrated and exhausted out of energy, right? You don't have to keep up with that, right? We all had a really great summer break. All of us get to reset. I get to teach this class a little bit differently. I can't really change things in April because I don't have the energy, but I do now, right? And hopefully same thing for you guys. If you can think about like, hey, what kind of student do I want to be? How do I want to organize myself? Right? You use those planners. I mean, I can't force you guys, but really, it'll help you, right? Hey, positive framing. Right? Now, this is I want to talk a little bit about metacognition. So think about how your brain works, how like what signals does your brain send to you, right? Uh, if you ever walk into a classroom and you're excited, like, oh wow, I really love this class and I'm ready for the challenges going to be sent towards me, that's really great, of course. If you ever walk into a class and you're just dreading it, like, oh, not this class again, I can't wait for this to be over, right? Recognize that and see if there's something you could possibly do about it, right? Like, oh, hey, maybe I can possibly change my mindset and get something out of this class or make something of it or find something enjoyable in it. If you can be engaged, I know I'm saying physics here, but maybe this is for any class, right? If you can be engaged in what's in front of you and make the most of your opportunities, then it's going to be a more enjoyable experience. You'll get more out of it, right? Probably more worth your time. Right. Good materials to have. All right, so this TI-30X2S is the calculator I have on everybody's desk. It's the one I'm going to use too. So if you ever wanted to follow along with the videos, it's what I got right here. This is about $10 or $15 at a store. If you have a fancier calculator like a Graphing, that's great too. But it's good to have a calculator. That's not your cell phone, right? Because we're trying to get away from using cell phones as much as possible, right? Planner, yes, please use that. Hey, something to keep notes in. The more active you are in this class, the more you're going to remember and the better it's going to be. Taking notes is one good method to do that. Let's look at this learning pyramid. So different ways of learning. At the top is more passive, and then as you go down, it becomes more and more active. I don't think these numbers are 100% scientific, but there's a lot of truth in this, right? Which is, if you just sit and listen to a lecture, how much are you going to remember, right? Maybe a little bit. I mean, if you guys just sit and listen to today, that's fine. That's fine. I know I'm going fast paced, just trying to get some principles here, right? But hey, if you read something, you're going to remember a little bit more. If you take notes, well, that's a little bit more active. Now you're going to remember a little bit more. I know sometimes I'll take notes on something and I'll look back, a day or two later, and it's like, I don't even remember writing that. Well, good thing I wrote it down. Otherwise, I would have no recollection of that even being said, right? If you can demonstrate something, blah, blah, right? The best way that you can learn something is actually to teach others. I know that myself, I learned this class really well by tutoring in college and then starting to teach this class too. Just learn it thoroughly back and forth. Right? You guys are going to have lots of lab opportunities. A number of days I'll have you guys in small teams like this for a number of reasons. Today I just got it for seeing chart purposes, but yeah, if you guys have genuine questions and you guys are asking each other and helping each other out, ask your lab partners, your teammates. If you guys are teaching each other, that's really like the best way to actually understand it yourself. Right? All right, a little bit more on metacognition. I think this will be the last slide we got to today. That's what I got to. Right. You might know about this. Save time. I'm just gonna skip to tell you guys how this works. Right. So let's say left to right is like, for example, how long you've been in a class. It's not exactly what it says, but let's make believe. So let's say you're in an 8-week class, and this could be like, I've been in the class for 2 weeks, and then 4 weeks, 6 weeks, 8 weeks. Okay, you guys get that 8-week class, right? Then how much did you learn, right? Let's say you sit down and you take a test, and your score is this green line, right? Now this is data from somewhere, I don't know, but kind of tells the story that I want to tell, so we're going to run with it, right? So if you sit in the class for 2 weeks, then okay, great, you scored like 11%, great, right? Now 4 weeks, ooh, now you learn more. 6 weeks, oh, even more. Sit in class for 8 weeks. Okay, now you know like 90% of everything. Okay, so the more you sit in the class learning, the more you learn. Okay, it's like a 1-to-1 correlation. That makes sense, right? Okay. Now the blue and the red lines are basically the same, so I'm just gonna kind of call them the same thing, consolidate this a bit. That's your perception. How do you think you did? Or how much do you think you know, right? Now, good to know, good to recognize that all of us have Homo sapien brains, and our brains are really good for a lot of things, and our brains also trick us in a lot of ways. And this is one of the tricks that's good to know, so you can know how to overcome this, right? I'm susceptible to this. All of us are, because hey, we have what we have, right? So how it works is, if you know a little bit about something, right? I've been sitting in this class for a couple of weeks, right? Your brain perceives that you understand more than you actually do, right? You think you score this much, but you actually scored way down here, right? Right. Then, and that'll continue pretty much until you actually are an expert in that particular field. And really only at that point that you become an expert do you actually underestimate the amount of information you know within that field. Why? Because now you know all the stuff that you actually don't know. You know all the unknown questions out there. You know how your field connects to all the other fields, right? But until that point, you tend to overestimate your own knowledge. That's what people usually reference when they talk about Dunning-Kruger. But there's another side to this, another aspect that I want you guys to see here. Now, this one's a little bit more abstract. It has to do with the slopes of these lines, right? Which is like a rate of learning. Right? Now, let's go back to the green line, which is actually what's going on. The more you learn, the more you know. Boom, right? That's like this very steep green line slope, right? You guys get that? Now, here's the really like insidious thing that your brain does, is your perception is a lot shallower, right? So if you sit down and study for like a half hour, let's say half hour every day, I'm going to study physics, Monday, Tuesday, Wednesday, Thursday, Friday, right? Which is a good thing to do, like break things up, study a little bit at a time, right? That's a really, more you study, the more you're going to know. That's the green line. But the red blue lines, that's like your perception. So if you sit down and study for half an hour and an hour, your brain is not going to immediately reward you with, oh, you know so much more now. In fact, it might say that you haven't. Right? It's just good to recognize. If you study, you know more stuff. There's the bell, so I'm going to have to wrap that up there. But you guys have a great afternoon. I'll see you tomorrow.